Now, despite their enormous diversity, programming languages and DSLs do share common lexical and syntactical structures. So during conception of new language systems, it would be beneficial to test and experiment with abstractions from existing languages in a plug-and-play fashion. This could also allow us to easily extend existing systems with new language semantics. This is where grammar traits come in to provide a unit of composition for mock rules and ASL actions. Similarly to classical traits, you can compose and describe requirements for rules and actions, as well as use aliasing, exclusion, and overriding to resolve conflicts. What is different about this workflow is the ability to abstract and generalize the subparts of your grammars so that they can be reused and composed in different ways. Here is, for example, the definition of message sense as a separate grammar trait. Notice that the definition focuses only on messages and does not include a specific rule for expressions. Expressions in this case are a requirement that can have different definitions in different grammars depending on the final composition. Just plug and play. In order to start using grammar traits to compose your recognizers, all you need to do is declare the usage of mock rules, the root grammar trait for mock definitions, in an otherwise normal trait. This will allow the system and the Gray algorithm to treat your grammar trait as part of an eventual grammar definition. Similarly, to define the grammar trait for your parsers, all you need to do is declare the usage of ASL actions. For example, here is how the entire Faro grammar included with lunch is defined using grammar traits. The lunch Faro parser is assembled the same way using grammar traits of ASL actions. This decomposition of both recognizer and parser into grammar traits does not only allow us to reuse parts of our language in other projects, but also to easily extend and evolve our grammars. Let's have a closer look at an example. We are going to extend Faro using grammar traits with the following syntax and semantics for classic control, including brace blocks for, while, if, and return statements, imperative or procedural style with syntax for imperative declaration of methods and variables, imperative invocation and bracket indexing, as well as functor syntax with function blocks and functor invocation. Each major category has two grammar traits, one for defining the mock rules and one for ASL actions. Each feature in the category is implemented by one or more mock or ASL methods. The resulting extending grammar composition has the following form. Notice here how naturally expressed are the composition semantics and how easy it is to resolve conflicts through exclusion, in this case, of core mock rules that are redefined in the three new grammar traits. Similarly for parsing, here is how to express the extended semantics and combine them with the original parser. This composition is even easier since most of the conflicts were already handled at the level of the recognizer. In order to use the new parser semantics and optionally the alternative syntax highlighting in your classes, all you need to do is use the grammar trait API as follows. Or to paraphrase Alan Kay, the best way to predict the future is to subclass from object using future syntax. Here the results speak for themselves. Check the extended version of the Smalltalk postcard that we saw earlier, straight out of a science fiction reality where Smalltalk adopted a more mainstream syntax. Remember that these are real-world byte-compiled extensions. Especially for this example, the extensions are completely equivalent at the bytecode level with the Faro-only version of the postcard. Of course, our example would not be complete if we didn't combine old and new syntax in the same method, proving that this composition can work the other way around as well, with mainstream languages adopting Smalltalk syntactic structures.